Everybody to our weekly colloquium. Today is a great pleasure to have with us Nikita Asterkhantsev from Google. As usual, I'm going to introduce a little bit his bio. So he's been a bachelor and master student at the Moscow Institute of Physics and Technology, and at the time he was working on lattice QCD. But then after the master, he decided to switch gears and place, and he moved to University of Zurich, where he got his PhD in 2023. His supervisor was Titus Neupert, and he worked on the theory of frustrating magnets. And then after the PhD, he went straight to Google, where he's now working as a research scientist in the quantum AI team. And today he's going to talk about the recent results and the recent advance in the Google Quantum AI roadmap. Nikita, the floor is yours.
Thank you for this great introduction, Dario. So I'm very happy to be here, and I will just straight jump back to the 20th century, and I would say that the great thinkers of the 20th century, they kind of laid the ground for the work that we're doing now. So, of course, the famous Richard Feynman told that, since the systems are classical, we should probably not break our head trying to simulate them, which is exponentially hard, but instead we need to try to bite a different bullet and build a quantum simulator, and then we can embed the system of interest into that quantum simulator. Then similar thoughts, although it's not really clear what Dirac meant in this quote, but some people think that he pretty much had the same idea in mind. And so this is what is regarding simulating physics, but also if you want like funding and more like practical real-world applications, there should be also some digital algorithms. And here, like one of the prominent people of the 20th century was Peter Shor, who first of all formulated his algorithm for factorizing prime numbers, which is now believed to be like, it's like one of the few quantum algorithms for which the quantum advantage is proven. And it has clear real-world applications such as breaking the RSA. And the year before, he laid down his work for error correction, so to combat one of the main problems of quantum computer, the errors. And so today I will tell you about our. In the 20. This is a bit slow. So in the 31st century, we all came together, and the many players who tried to kind of build on top of the shoulders of the giants and create this quantum computer things. And today I will tell you about our recent works in the area of error correction, in the area of quantum algorithms, and in the area of physics simulation. So some of these topics I will go very slowly. Some of them I will just quickly flash because we probably don't have time for all of that. And then let's begin with the quantum error correction. And I was told we're going to have a lot of undergrads, so this lecture should be really introductory. Graduate students. Okay. Well, this is better. So I'm gonna give some short introduction to error correction. That will tell you about our results about the single logical qubit. So we have this roadmap which kind of ties together system developments in the what accounts for error correction, and it's tied to development in applications, so in theory, and in the access for internal users. So we need to move along all of these three axes, so to say. And what is quantum error correction? So the idea is that you have your physical qubits, which are, depending on the platform and depending on the setup, they are error rates from 10 to minus 2 to 10 to minus 4. But this is way too high for any practical algorithm, such as breaking the RSA or anything. You need to somehow reduce these corrections. And on the device and the hardware side, there's no solution inside. So what we could do, we could use redundancy, right? So we could pile many of these noisy qubits together, and then if they're individually not too noisy, then by piling them together and using this redundancy and spreading quantum information over a larger chip, we can sort of try to prevent it from being lost. So how is it actually done? Well, so this is the only technical slide that's going to be in this part of presentation. But so please please stay with me. So the idea, I will only speak about, I mean, probably many of you know many other correction codes. I will only talk about the surface code. So what is the surface code? We're gonna imagine you have a system of your qubits, and you have a very large Hilbert space, 2 to the n. So in this Hilbert space, we'll define operators which are called stabilizer operators. They form stabilizer groups. So all these operators, they mutually commute. And so since they all mutually commute, you can diagonalize them all simultaneously. And so the number of those operators will be exactly n minus 1. So the idea is that after you went to the joint eigenspace of all these operators, you still have the Hilbert space dimension of size 2, and this is the Hilbert space dimension that we will associate with an encoded logical qubit that sits on this chip. And so in the case of surface code, the stabilizers are either 4Z operators in the like darker plaquette, 4Z operators applied to the data qubits. Data qubits are always going to be in yellow, or 4X operators applied to the data qubits. This is going to be in less dark blue. And so what is left? You still have. So like I said, you have this Hilbert space of size 2, which encodes logical 0 state and logical 1 state. And we still have operators which act within this small Hilbert space. So how do these operators look like? These are logical strings. So logical X and logical Z operator. There are many ways to construct them, but one explicit way to do it is like you take a vertical slice of your code from bottom to top, and you multiply Z across all of your size going from bottom to top. So what you can see is that this operator is going to commute with all stabilizers. So if you apply this operator to your small Hilbert space, it's not going to kick you out of this manifold. So you're going to stay there. So and what's also important is that this operator, they anti-commute. So they form the correct algebra. So you have your Hilbert space, you have operators which look like the Pauli operators of a single qubit, so why not think of it as a logical qubit? And you can think about it in the following way. So this was our full Hilbert space, and in some far, I know it's a little bit incorrect to think about it, but in some far corners of this Hilbert space, there are your 0 logical and 0, 1 operator. And if some error happens and it pushes your state away from 0 somehow here in this bulk, there is a smart machine on top of that, a decoder, that will detect that and push your state back to where it belongs. And there are these very large, super non-local operations which allow you at will to go from 0 to 1 and back and vice versa, and create some other operation, other states. Okay, so like I said, imagine you have, let's focus first on some small patch of the chip, and then bam, there happens the Z error. So your chip got entangled with the environment, and somehow this spin acquired a phase. So this stabilizer will become unhappy and will get multiplied by -1. Or otherwise, you have this stabilizer, and then there happened an X error on a qubit, then this stabilizer will also become unhappy, will also get multiplied by the -1. So since you flipped the spin, the Z, this product of 4Z will get multiplied as a whole also by -1. So this set of stabilizers, they really allow you to detect errors when they happen on the chip. And also if you measured all of your stabilizers, and the results of those measurements are called syndromes. So once you know all the syndromes, you can look at them and you try to guess where the error happened. Because in reality, decoder doesn't know the position of this location, it only knows which plaquettes are happy and which plaquettes are unhappy. So let's look at it in a little bit like more. Okay, so before that, let's see how actually the logical qubit works. So first we prepare our qubit in logical state 0 or 1. Say we prepare in logical state 0, and then we apply every microsecond an error correction cycle. So what does an error correction cycle do? It applies these 4 layers of CZ gates, and then it measures the blue qubits. So essentially what happens, it forms these stabilized operators, and then it measures all of them, and it collects the syndromes. And once you collected the syndromes, there is a decoder in real time. It gets this the results of these measurements into itself. We use some maximum likelihood function to predict where the errors and which errors happened, and then it applies the feedback, so immediate transformation to undo these errors on the fly. Let's look at some examples. So, okay, I'm a decoder. I'm getting fed some syndromes. What am I going to do? So, okay, imagine errors happen here, but as a decoder, I only know those two plaquettes are unhappy. So I need to guess by maximum likelihood where the error happened. I mean, okay, no-brainer. Those two are unhappy. So the light blue. So it means the X error happened, and it probably most likely happened between those two plaquettes. So I'm just gonna flip back this single qubit and fix my code. So no problem. Yes. Mm-hmm. Yeah, the phase of the logical qubit currently we don't worry. So I mean, yeah, because we can have this is my intuition too. You can have like a magnetic and electric charge created, which can behave like a fermion, and then they can acquire some phase, and then you undo them. But the phase of the logical qubit, the global phase, you mean? This we don't care about. Oh, you mean so if we had 0 plus 1?
Sorry, yeah, something like that. So if you have superposition, if you flip spin up and then down, you acquire usually unknown. Like up, down, plus down, up can become up, down, minus down, up, or something like that, right?
Let's discuss it. Let's discuss it later. I think I will answer your question. All right. So let's consider a more difficult scenario in which we had two errors happen here, and the funny thing is that the decoder now, the syndrome of this plaquette is now fine, yeah, because it has even number of errors. So when these two qubits flip, the product of all those 4 Z's is still fine. So the decoder will only see that this and this plaquettes are unhappy, but still by maximum likelihood you can deduce that that those qubits were wrong, and you can fix them as well. But then a difficult situation happens when in a situation like this, when for instance the string is say this code is size 7, so it's a 7 by 7 lattice, and when you have slightly more than a half, say 4. In this case, only this syndrome is unhappy. So you can check all other syndromes are fine. So what the decoder sees is only this, and it doesn't know what to do. It doesn't know how to complete, and it's not even obvious that you need to undo it this way. So the decoder most likely will deduce that probably those errors happened, and we will complete them, and the decoder will finish the job for the errors, and the decoder will flip the state of our qubit. So we will essentially apply the logical X operator to our qubit. So this is how we fail. So the goal is that this many errors never happen during a single cycle. In such case, we can always undo them. So now let's look at the results. This is funny graphics for the paper, whatnot. So in the work of 2024, we'll take the code of size 3, size 5, and size 7, and we will increase the size of this codes, and we'll look at the logical error rate. So the probability at each cycle that the decoder actually will die and will flip the state of the qubit. And this logical error rate is described usually by this formula, so some epsilon naught, and most importantly is this scaling factor. So the scaling factor lambda to the power of d plus 1 over 2, it pretty much tells you is your logical qubit getting better once you pile in more qubits? Because it paradoxically, if lambda can be so bad that once you increase the size of your code, you actually only make it worse. So it's better to use your physical qubits instead of logical qubits. So in 2023, the first work was reaching break even. So the logical qubits of size 3 and 5 got the same logical error, so which means lambda equals 1. So what happens is that in that case, you fix the number of quantum error correction cycles that you run. You run your error correction cycles for you run your error correction for this many cycles, and then at the end, you read off your logical state. And if it flipped, you say it's an error. If it didn't flip, you say it was all great. But then in 2024, there is now solid advantage over having physical qubits. Now we have lambda equals 2. So this is the logical error rate as it decays with the size of the code. You see it's very robust exponential. And we can also look at this plot here. What this is logical error probability as a function of quantum error correction cycle. And these in black are the results of the 23 paper. So you see like the logical error probability almost immediately shoots up, and this is low quality. Instead, the distance 3 code behaves like this, and the distance 5 code already outperforms the physical qubit. And the distance 7 code, it performs even better. So the main reason for this improvement was actually improved T1 of the new device. The previous device had the T1 of 20 microseconds. Now this one had the T1 of about 80 microseconds. And of course, like improved CZ gaze, because all these things that you do to measure syndromes, they also contribute to your error. So on many of these fronts, there was a battle. Also improved the decoder, which led to these results. I also need to say that the real-time decoder that I told you about was like an idealized picture. The real-time decoding only happened in the experiment with the 3 and 5 distance. With the 3, 5, 7 scaling, it was post-decoding. So the idea is that all of these syndromes and all of these error models and all of the corrections that we apply, all of them are Clifford operations. So pretty much what we can do, we can run the whole experiment, and we can just read off the states of syndromes at every step, and we can just memorize them, and then at the end we can emulate how this particular decoder would behave in this system. So we don't have to decode on the fly to know how potentially the algorithm at its best is gonna behave. But with 3 and 5, it was actually real-time decoding. All right, so how much time have I spent on this? Oh, it's actually not so bad. Okay, so error correction is moving forward. The next step is, of course, the 2-qubit logical gate. And now let's go towards applications. And of course, in case of what you see here, it's an application. Of course, it's debatable. Some people will say, but let's put that into perspective. And so we can pretty much try to arrange all of the different tasks which could be based on, say, random circuits. We can arrange them into the following hierarchy of so-called goodness, or I don't know which the right word to pick. So the bad problems are non-reproducible and non-verifiable, such as random circuit sampling. So the problem is that once you sampled some bit strings and you are at the beyond classical chip, you don't know whether your computer is working right. You don't have no way to kind of benchmark the fidelity of your device other than extrapolating from smaller systems. So it's non-verifiable, but it is also non-reproducible, because if you run this experiment the next day, you will not have the same set of bit strings. There are experiments which are reproducible, but still non-verifiable, such as beyond classical local observable. In such case, you can run the experiment tomorrow, and you can hope you will measure the same number. If it's just one number, you can measure it tomorrow, it's going to be the same. But it's still non-verifiable, because if you measure like beyond classical observable, you can only hope that by some extrapolations of your fidelity or SNR that you are not measuring trash. And final case is the reproducible and verifiable problems, and we are not there. And one of them, for instance, is Shor's algorithm, or so-called peaked circuits. So the idea with this green set is that I generate some data set. I know the answers, but then I forget them. Then I ask the quantum computer to give me the answers, and then I can remember those answers, and I can compare what the quantum computer gave me. So in case of the Shor's algorithm, I will generate a very large number, which is a product of two very large primes. I will forget those primes, but I'll write them down somewhere. I'll ask the quantum computer to give me this factorization, and then I can compare that the results of, even though the task itself is beyond classical, I know after I got the result, I know whether it's correct or not. So this is the good thing, and we are not there. But okay, so what is the? So let's start from the left, the red problems, and let's talk a little bit about this XZB benchmark. So what is the idea? You have some ground truth. Ground truth is the distribution function on the bit strings, and this ground truth is encoded by some ideal quantum circuit. So you have just some qubits, you have some gates applied, and you know what is the correct distribution of bit strings on this circuit you're going to have. Instead, you have some sample, either generated by a quantum computer or by a classical computer, and then you can overlay these two distributions, which produces this so-called XZB benchmark. And under some assumptions, this XZB benchmark gives you the fidelity either of your device or of your classical simulation. And then, but you know, there are always these headlines like, oh, you know, the Google's quantum computer did the task in septillion years. What is the task? So the task is, there is some ground truth, and the task is to generate a sample such that the XZB with that ground truth is over some threshold. This threshold is also given, say 10 to the minus 3, whatever. I just give you a threshold, and then the task is to generate a sample with this threshold, and it should be big enough such that the error bar is smaller than this threshold. If I give you, you know, if this threshold is too high, for instance, a quantum computer cannot generate the sample at this point, so, but also in some case cannot a classical computer. And you know, the quantum computer has some discounts. So why this threshold and not 1? Because the quantum computer has decoherence, has gate calibration problems, and readout. At the same time, you know, classical computer can also leverage this discount and can do some truncation in MPS or drop some slices and dense network contraction or do even some gate removal or whatnot. And now, you know, since we compete against the classical simulation methods, I just wanted to tell you what you know, what is the main competitor for all of these problems on the side of the classical methods, and why it's actually not always so easy to know how much it would take a classical computer to generate this sample. So you know, you may have remembered that 2019 Google came up with the claim that some simulation would take like over 1,000 years on the Frontier supercomputer, and then the number went down in a few weeks because something better was found. So what was that thing that was found in that case, and so why these numbers, why they can go down? Well, you know, so what you all know from school is how to simulate circuits using state vector simulation, right? So you have some initial state of you have some initial bit string, and then you apply some gates, and then you eat your circuit left to right. This is a very, very efficient method, the most computationally efficient method to simulate circuits that have high entanglement. But the problem is that you need to store kind of this whole construction. So you need to store 2 to the n of your 2 to the n memory, and at some point it becomes prohibitive, and you cannot do it anymore. But you know, actually, the number of qubits is not what sets the complexity of the simulation. It's something else. Consider this example, but you know, I was lazy making this. But consider like this actually is very, very long. So many qubits. But how much memory you need to simulate this circuit? You can simulate it by using just a few bits. So what happens is that I will first contract this part of this green area in the circuit. I only need to store the answers at this leg. So I only need to store the Hilbert space dimension of size 2, and then I can move it to the right, so I can also eat the circuit up from left to right. I never need more than two bits of memory. So you see there is something else which controls the complexity of the computation. It's not the number of qubits. And the method with the generalization of this cartoon that I've just shown is called tensor network contraction. So the idea in this cartoonish circuit is that we need to compute this amplitude. This is just a scalar, but it's written in form of this circuit. And then, you know, we unite tensors in some groups. We contract them, we unite again, we contract again, and then we end up with the scalar. Now, the interesting thing, and I'll go into details of that a little bit more, is that finding the order in which you annihilate these tensors, in which you eliminate them, the correct order, the optimal order, is an NP-hard problem. So pretty much at every step of this algorithm, you take a bond and you eliminate it. You contract it, so you remove the summation at some bond. And if you have, order n times number of layer bonds, you have all the possible permutations, which gives you all the possible orders how you can contract. So it's not so easy. And we can illustrate that by contracting this graph in here. So this graph, I don't know how well it's visible. These are 5 points which represent tensors, and these tensors are connected to other tensors by legs, and these legs, they have indices on them. And this graph can be also expressed as leaves of this tree. Yeah. So each of these brackets represents a tensor, and these letters, they represent which edges kind of go out of this tensor. And then what you need to do, you need to create a tree from those leaves, and you can kind of at each step you can pair the kids at the same level, which has the same index. You can pair them and you can annihilate the index. And this pretty much encodes all possible contraction orders that you can do on this graph to arrive at the final scalar. So you see at the top there is nothing, so it's just it's a scalar, so you contracted the whole thing. And you can see that these two trees, different contraction orders, they differ. And the difference is that in this lower contraction tree, there is this big tensor, which has 6 legs, that other tensors, that in this case was not present. So you see that usually complexity is pretty much determined by this largest tensor. It's the hardest to store, and it's also hardest to operate with. So this to demonstrate that the order of this contraction really matters, and you can see in this example that it can be from easy to hard. And this is what also happened in 2019. So the initial estimates, if you run Catengraph for longer and you apply some more sophisticated algorithms to find the contraction path, you could lower the claim time to like 200 days. And you can even improve that. I will not go too much into details, but the idea is that if you only need to compute amplitudes for a particular set of bit strings, so you need to compute for 1 million of bit strings, you can say like, okay, for this qubit, or for those 3 qubits, I only have this combination of zeros and ones, so I will already simplify it and I will push that into my circuit, and I can eliminate some of the tensors at the edge of my circuit, and this can further reduce the simulation time to 300 seconds. So you see that we went from 10,000 years to 300 seconds. So these numbers, they really can fluctuate wildly. And yet, as the time goes, a new paper, a new device, new benchmark, and now in the recent work which came out on Archive last month, I think the numbers are so high that they don't even fit in this graph. And then it's still possible that they will go down at some point, but they kind of, since like recent couple of years, the rate of at which these numbers go down on the classical side is sort of decelerated. So we think that the classical methods, they start to reach the optimal capacity that these heuristics for finding optimal contractions can have. Okay, so that was random circuit benchmark, and that was sort of answering a question that was never asked. So let's try to answer a question which could be asked. And the next step is, of course, like, can we also have a random circuit, but now we don't measure the distribution of bit strings, but instead we are focused at an observable at a particular site. And then this observable, in some cases could represent maybe something useful. And so, of course, I'm gonna talk about out-of-time order correlators, which are represented by this nice picture, because in the out-of-time order correlators you have a butterfly, and then like a butterfly wing here in São Paulo can cause a tornado in Texas or whatnot. So let's study this effect and also try to make that one beyond classical. And so okay, we want to make our quantum computers practical. We want to extract some use from them, and in order to do so, the first task we could do is the Hamiltonian learning. So you have some unknown system, say a molecule, and then you only have access to the results of the experiments with this molecule. So you can hit your molecule here, you can read off the response there, and you can keep repeating that many times, and you want to understand actually not the times between this hit and response, but maybe you want to understand some parameters of the Hamiltonian describing this molecule. But how do you do it? And so the way you can do it, you can replicate this Hamiltonian on your device with tunable parameters. And now you can tune the parameters of your device such that to recover that response picture of the molecule. And once you know these parameters of your Hamiltonian, you can predict something about what were the parameters in the actual molecule. And for a quantum computer to be useful in this task, what you need pretty much 3 requirements. One of them is that the response that you're measuring is not vanishing, so it's measurable, because we have some particular short budgets. If the response is like 10 to the minus 6, we can never measure it. It should be sensitive to the details of this Hamiltonian. For instance, if you hit here, you read off there, but somehow it doesn't depend on any details of the system. This response time is always the same. You cannot learn anything about your system. And finally, we want to say, okay, a quantum computer is useful, so it should be able to do something that a classical computer cannot. So we need at least a molecule or the Hamiltonian such that a classical computer cannot tackle. And I will not go too much into proving what's hard or what's not. I will just tell you about the observable that we built for this case. So actually, it may it may sound not so difficult. Like, okay, you prepare your initial state, you time evolve it, you apply some gates, and in the end you measure an observable. If you apply sufficiently many gates and your system is sufficiently big, then at the end to classically say what was the value of that observable is of course very hard. Now there are 2 problems with that, and there's actually one problem. We need to measure that observable, and so this observable, it will become small for 2 reasons. So first reason is that once this circuit has many gates, the state of the system becomes very thermal, becomes chaotic, and all of these observables in the final state, they exponentially go to 0. That's one problem. And the second problem is that once you apply too many gates, your system becomes very noisy, and this also drives that observable value down. And so if you combine those 2 factors together, it's actually not so easy to build a circuit which will generate a measurable observable that will be able to measure, that otherwise will be classically hard to compute. And so this out-of-time audit correlator, so the idea is that we prepare our initial system, we time evolve it to the future, so we apply some unitary, we hit the butterfly operator, and then we come back to the past by undoing the time evolution, by doing U-dagger, and then we probe what was the effect of that wing of the butterfly in the present. This U time evolution matrix is given by the repeating layers of 2-qubit and single-qubit gates. The 2-qubit gates are the best for us, so FSIM gates, native gates, and the single-qubit gates are drawn from random SU2 ensemble. And so while if this time evolution is short, what happens is that the time evolved in Heisenberg picture butterfly operator, it does not overlap with the measurement operator. And so the result of this computation is always 1. So it doesn't depend on any parameters of the circuit. It's just 1. On the other hand, once the butterfly operator, time evolved butterfly operator starts to overlap with the measurement operator, at this point we start to get some response, and then these curves they go down. And the funny thing is that spatially separating butterfly and measurement operator creates this gap between the lag between the moment when the signals they become to decay and how many gates we can pile into the system. So at least by this technique, we can make left-to-right simulation of the circuit very difficult, because this U and U-dagger, they're going to have a lot of gates, and they will generate like a huge entanglement barrier to get from the state to the butterfly and vice versa. Even though maybe in poly picture, in the operator picture, the simulation may not be so difficult, but at least the state vector methods will all fail. And like I said, the important thing is that the results of this simulation is they depend on the parameters of the individual gates. So what we see here in the experiment, we put the butterfly operator at a particular position on the lattice, and then we apply some number of cycles, say 12 cycles, and then we measure the measurement operator at all different positions of the lattice. And then we see what is the distribution of answers once we vary the single qubit gates in our system. And so you can see that if the measurement operator is very close to the butterfly operator, then as you saw from the previous slide, all these curves are going to be here in the zero. So there is no variation with the details of the single qubit gates. All of them are zero. And if the butterfly hasn't reached the measurement yet, all of them are going to be 1. But there's actually some life happening around these curves. They don't all decay like this. They all decay slightly differently, and this is the region that we want to capture. So predicting each of these, maybe predicting the mean of this curve is actually not so difficult, but predicting each of these individual curves for a particular single qubit gate realization, so this was going to be hard. And first of all, we show that as we increase the system size, as we increase the depth of the system, the size of this fluctuations at the front, fluctuations with the circuit instance, it does not decay too fast. So we, at least in the experiment, we can see that they decay sort of polynomially, although we don't really draw any particular extrapolation through that, but there is hope that once we go to beyond classical regime, there is going to be something measurable. And here I just wanted to present you our first candidate for the beyond classical local observable is the OTOC experiment, in which we put the measurement operator at the bottom of the circuit, and the butterflies are acting simultaneously at the top of the circuit. So this is 95 qubits, 1,000 gates, and this is how what we measured for each of the individual circuit instances. So we checked diligently that it's hard to simulate going sort of from left to right. We have very good understanding of the reasons for our errors. We have systematics and short noise under control, so we project the SNR to be of order 3. But can something be done in the operator space? So what happens if you actually time evolve the butterfly operator? And for that we devised a new technique. I'm not gonna go too much into the details of that, but the idea is that since now in OTOC we go forward evolution and we go the backward evolution, and so the butterfly operator, it happens in the bra, but also it happens in the cat. So we have 2 copies of time-evolved operator now. And this allows us to construct this sort of quadratic form. This is how OTOC is built. And if we could sample the content of our butterfly operator in the Pauli basis, if we could sample it from this distribution, we could measure this observable. And so this is actually new. This is new for OTOC. You don't have this in a time-ordered observable. That one will not form this positive measure like this one in OTOC. So this one in OTOC forms this positive measure, and actually we devised an algorithm that allows us to semi-efficiently sample from this distribution. So just the OTOC to the first power is probably can be improved as a candidate for quantum advantage, and for that we use OTOC to the second power. So the OTOC to the second power, what that is, we go to the future, we apply butterfly operator, we go to the past, we apply measurement operator, but then we repeat it. So we again go to the future, we apply butterfly operator, and we again go to the past, and then we measure the measurement operator. And so now what happens is if you write down the OTOC, the trace in terms of the Pauli operators, now you have 4 copies instead of 2. Then instead of, in addition to the diagonal contributions, how we call them, where you need to pair the content in the left copy and in the right copy, now there are these long loops of 4 operators which are not dependent on each other, and this leads to a severe sign problem, and that's why we believe this is hard to simulate, at least using this new Monte Carlo method that we came up with. And so this is the result. This is the kind of the proposition for the final beyond classical experiment, in which we measure OTOC square. This is the actual experimental result. We put the measurement operator at the bottom of the chip, and we have 3 butterfly operators here. This is the experimental data, and it has 2022 qubit gates for every of the circuit instances, and to simulate each of them using our best in-class tensor network contraction algorithm and our best in-house developed system to find the best contraction, so to empirically solve that NP-hard problem, we still find that it would take 3.6 years to contract each of these circuits. So you can see numbers kind of went down substantially from the RCS, because now here we actually need to care to have circuits with measurable signal, but still we managed to find circuits that have this large number of years on frontier. And like I said before, we have reasons to believe that we have our systematics and statistical noise under control, and that this plot here on top, the noise is at most 50% of the true signal. So the signal divided by noise in this circuit is 2. Okay, and now, so we started, let's switch gears completely once again, and this will be the last part of the talk, and I hope we can exhale, and now we can just relax and talk about some physics. So like I said in the very beginning, the first, before sort of Shor, the first ideas, the propositions to apply a quantum computer, they were coming as a tool to simulate physical systems, because you have your condensed matter problems, and I'm also in this business. So in my grad school, I was applying frustrated magnets, and it's all very hard to simulate. It would be just so nice to put it on a quantum computer and embed it to the chip and run your time evolution, but just like in the hardware, and read off some responses or whatever we want to study. And this was the effort of the last year, and with the paper that we published. This year is actually related to that, and this is our effort on the analog simulation. So again, this is the picture, the representation of an artist of how they see combined digital analog simulation. So what is the problem with a digital simulation? In a digital simulation, what we do, at every layer of the circuit, we split all qubits into pairs, and then we move the coupler between the two qubits such that for a very short time to create a pulse, entangling pulse between two qubits, and that's how we apply gates. But we sort of only because you have your chip, you split them into pairs, so you can see that only sort of 1/4 of the bonds can be active at a time, because you want one qubit to talk only to one other qubit, or only to one other coupler. You cannot do more. So it leads to you need to wait longer, like physically longer, to apply the same amount of entanglement in your system. So you accumulate more decoherence, so your system has more time to get entangled with your lab. So the picture of that is here. You have two qubits, and then the coupler moves up and down, but the idea is that this qubit doesn't talk to this qubit, ideally. And this qubit only talks to this qubit on the right. And otherwise, what we could do, we could turn on all couplers simultaneously. The good thing is now entanglement now grows 4 times faster, so the decoherence is potentially big coherence is much smaller. But the problem is now it's way harder to calibrate the system, because we have some temperature fluctuations, we have 2-level systems, and so for every time for these gates, before we run the new experiment, we want to say apply a particular I-swap, we need to calibrate every time. So we cannot just take the shape of the pulse that we used last week and apply it. It will give you something which is almost like the I-swap, but if you want the swap rate to be like exactly 1, you need to run a bunch of experiments. Before you run your big experiment, you run a bunch of small calibration experiments, and you check that today this pulse gives you exactly the swap rate 1. And then you can proceed to whatever OTOC, RCS, or something. But how do you do it here? If we want, say, all of these couplers to be 10 megahertz, all of them uniformly, how do we do it? This is very complicated. I'm not gonna go too much into the details how we calibrate the system, but is actually possible. And the idea is that we single out the part of it. So we have our qubits. There is one coupler in between them, but there is also above the rest of the system. And we put the boundary around those qubits to the idle, so the photon cannot escape to the rest. And then we do some measurements, and we actually we run some sweeps, and we manage to deduce all the parameters of the system. But I'm not gonna go too much into the details. So, but also what we need to understand is that our chip it's a Bose-Hubbard model. So we have the transmons, but the transmon, it can have 0 photons, it can have 1 photon, it can have 2, 3, etc. So it's a many-level system, and also is the coupler. But what we want to study, we want to study some nice spin model. A spin model which doesn't know anything about the couplers, which doesn't know anything about higher order states, which only is formulated on the physical qubits, and only in terms of the two-level systems. And so once we try to do it, so we project our full Bose-Hubbard model onto the spin model. What we get is pretty much what we want. So we get the local disorder terms, which are written down like this. We have the XY interaction between the sides of our lattice, but we also get stuff which is pretty unusual. Yeah, so we got also the ZZ, but then we also have longer range hoppings, and we have longer range density mediated hoppings. So if you have a photon here, you don't have a photon here, the swap rate is different. But those terms are controllable in their magnitude. They're controllable by the swap rate divided by the harmonicity. So in principle, we can always go to the regime of slow dynamics where all of these higher order terms are absent, and we only have the good ones, the local disorder and the XY, and then you can study your favorite XY model on the square lattice, which we actually do. So we take our system, we first start with the disorder in the checkerboard pattern, and then we put the photons to where the spins, to where these magnetic fields, they point down. So we prepare the ground state of our initial Hamiltonian, the Z staggered field, and then we ramp down the magnitude of this staggered field, and we ramp up the magnitude of the interaction between the qubits. And so pretty much what we want to do, we want to prepare the ground state of the XY model using our analog simulator. And this is the results that we have here on the left. We apply post-selection on the photon number. It allows us to go under the Kosterlitz-Taulitz transition. So this is the ground state energy, and it's hard to get there. The red curve is the experimental data, and you see first as we increase the ramp time, so we increase the speed at which we go from the staggered Z Hamiltonian to the XY Hamiltonian. The energy improves, but then it's supposed to keep going down. But actually, at large ramp times, what happens is that this energy begins to lift off again. It means the evolution time is just too long, so system just starts to decohere. So there is always this sweet spot. And for us, the sweet spot turns out to be slightly lower this so-called KT transition. So just very quickly, the idea of the KT transition, in the XY model, there are these global textures called vortices, and a vortex has some core radius A, and depending on the full size of your system and the core radius of this vortex, the energy to have a single vortex goes logarithmically with the ratio between the system size and the core size of the core of the vortex. At the same time, if you have a possible vortex of size A, you have this many ways to kind of place it in your system. So you have the interplay between energy and entropy, and if you put all that into the free energy, this is the expression that you get. And it's funny that actually in 2D, this bracket kind of factorizes, and you see that the free energy switches sign depending on the temperature. And so this is what's called the KT transition, and it's very interesting to go under, because under the KT transition there are no free vortices in the system, and above the KT transition there are vortices. One of the ways to diagnose undergoing the transition is to look at the correlation functions. So here what we look on the left, we take a spin in the middle of the lattice and we measure the XY correlations to all of the other spins in the lattice. We see that if the system is prepared using the slow ramp, the fast ramp, so it's hot, then the correlation functions, they decay exponentially. But if the system is prepared slowly, if it's a slow ramp, then we see that this correlations, they, at least for this intermediate regime of distances, they decay polynomially. So we take all of this syndromes of the KT transition to the same slide. So first of them, of course, the energy is below, which is good. On the other hand, we have this joint. We just fit the correlation functions using this joint fit. So we have the sum of power decay and the exponential decay, and we see how the fit distributes the weights between exponent and the logarithm. And then we see that once we go to long ramp times, then the power law wins. At the same time, the decay, after we have this polynomial decay, we can extract critical exponents, and the critical exponent that we get corresponds to the right phase that we anticipate. And finally, the total density of vortices. So a vortex operator for us is the sum of currents around the plaquette. The density, total density of vortices also sharply decreases as we increase the ramp time. Okay, and then this is not the only thing what we can do. Yeah, so initially we sort of started with a very simple state where we put photons at a particular position. So we were targeting the ground state. What one could also do, one could misplace these photons initially. One could place them in the positions where the field was actually going up. So one can control the initial energy of the state. But the problem is that once you arrive at your final state in the XY model, your system is sort of already thermalized. So all the interesting dynamics kind of ended, and all the observables in the final state are predictable by the eigenstate thermalization hypothesis. Can we somehow create some interesting textures and observe thermalization in the real time? And we actually can do it, and we come up with this technique of tunable dimers. So before we turn on the XY evolution of our system, now we don't even have any staggered Hamiltonian initially. We just take the qubits in our system, we apply this gate, so we create some texture using either hot dimers, the cold dimers. So here you can make it either a singlet or triplet. It creates energy currents, creates spin currents, creates vorticity. So you can create some interesting state, and then you can immediately turn on the XY model, and you can look at thermalization in the real time. So first, what we did, we made in our system we made all of the dimers cold. So it's not the ground state, yeah. So you have most of the energies are zero. If you apply the XY term between the dimers, it's always zero expectation value. But for some of the terms, it's actually -1. So it sort of brings you halfway to the ground state. And then we see the system quickly thermalizes, and the observables are predicted by the ETH. Instead, what you can do, you can put hot dimers in the left part of the system, and you can put cold dimers in the right part of the system. So it's actually a very high energy state, but we can see it takes really a long time for the state to thermalize. And the thermalization of the state is very well described by a simple diffusion model, which is fitted by a single parameter, the diffusion coefficient. So, and this is hard to simulate, for instance, using MPS. Of course, there are many other ways to obtain the diffusion coefficient, but it is sort of a pathway towards an interesting practical computation targeting some properties of the physical system using the analog regime, because we can create some initial textures in the lattice which are long-lived and that tell some information about some fundamental properties of the model, such as diffusion coefficient or something else. So it brings me to the end of my colloquium, and I started with the foundation of the 20th century, but also like the demand, and in a way we are working on fulfilling that demand, on satisfying those founding fathers of quantum computation. So we have some progress on the algorithms, although now mostly it's random gate-based RCS or OTOC. We have very substantial progress on error correction, with now a single logical qubit working very well, and now moving towards logical gates, and we of course can also now simulate physical systems, which is, I guess, is of the biggest interest of this community, and we will keep working in that direction as well. Thank you for your attention.
Okay. Thank you very much. Time for questions. Let's start with the youngest.
First of all, thank you for your nice talk. So about your talks, I was wondering which kind of operators are these butterfly operators? Like you choose them like as I want?
Yeah, in principle, it could be anything. For us, we picked anything which is a single Pauli string, because these kind of operators are easiest to apply. We just, through the microwave, we apply pulse to one qubit or to several qubits, but it's like just I mean, in this work, we use it to be single, like a product of single qubit gates, so a Pauli string. But it also could be 2 qubit gates. It doesn't really matter for the, for the setup.
In that sense, the measurement operator depends of the which one I'm choosing to be the butterfly one, right?
Well, I think one could cook up a case where that would matter, but since our circuits are almost like drawn like this in the individual constructions, we have the single qubit gates, they are random, so they don't respect any symmetry. I think actually for any pair of butterfly and measurement operator, the qualitative conclusions will be the same. It's like if you had a circuit which, say, conserved charge, and then you had butterfly and measurement operators to be both Z, then here you could run into a problem because something would commute. No, actually not necessarily. But I mean, if it's like Clifford and something, then maybe you could be careful. But in that case, I don't think so.
Oh, and how are you tracking the amount of the OTOC? Because the OTOC is not the observable in the the way of observables, everything. So how are you like tracking the quantity?
Oh yes, so
to do the plots and
yeah,
everything?
so there is a trick. So you can of course measure using the ancilla. So the thing is, OTOC in the form like expectation of BM. It's not written as an expectation of like an emission operator. So in this way, you cannot just measure it. But there are 2 ways. So in 2021 paper, we measured it using the ancilla qubit. In this year's paper, we actually do something more easy. So the initial state that we have, the initial psi, we take it as an eigenstate of the measurement operator. So in such case, the OTOC simplifies to having psi, U dagger B U M, U dagger B U, and psi. So this M, which was staying here on the right, it just fell off. And then you can prepare your psi final, which is U dagger B U acting on the initial psi. And after you prepared this wave function, you just measure M.
Okay.
But it's really not too much like the reduction of generality, because I can later tell you that you can measure it with M. It doesn't have to be the eigenstate of the initial state. You can measure it using ancilla.
Okay, thank you.
Maybe I'll first say some rant and then I ask a question. So I think this is like complete confusion. Butterfly effect has nothing to do with whatever, this OTOC, Lyapunov exponent. And we all know it. I don't know who said that and why said that. You know that if you do it in the bottom of the ocean experiment, where Lyapunov exponent are bigger, you won't see any effect. If you take a piece of metal, electrons are super fast there. You can hit it with a hammer, not a butterfly, and there will be no tornadoes. It's really total confusion.
We should discuss.
So chaos in atmosphere is described by kinetic equations, which have nothing to do with quantum error, which doesn't have Lyapunov exponents or classical and so on. Anyway, and then my question. So it's about your third part of the talk. I really like it. So, but diffusion, it's true, as far as I know, computing diffusion coefficients is very difficult, but at least theoretically we expect diffusion. I just wonder, are you like, can you move to sort of a borderline where like there are debates even what's going on? Like if you say start increasing disorder or whatever, then people start arguing whether there is a subdiffusion, whether there is a localization, whether there is some glass behavior. So is it maybe realistic, or do you have any plans to go in that direction?
Well, I'm not sure about the plans, but it's of course realistic because we can engineer any disorder in that typical Hamiltonian that I showed here that we work with. We have very good control over those first two terms. So we apply voltages to our initial qubits, and then based on that we derive the effective spin model. So we don't know initially what these parameters are going to be, but there is a way we can tune them to be almost anything you would prefer.
I guess you said, but what are kind of characteristic time scales where you don't worry about decoherence and so on in terms of couplings? Is it like thousands or?
Thousands of inverse G?
Yeah, something like that, or even longer.
Well, no. Can we try to plug in? Because I'm getting afraid it's going to die. Oh, thank you so much, Dario. So it's very good that I did not delete the slides. I left them. I didn't even put the invisible mode on them, so they will show. But it's great that you asked this question. So we actually did the XZB benchmark up to 35 qubits. This is time in inverse G as a function of system size, and this here is measured the error rate per qubit per cycle. So it's about 10 to minus 3. If you recompute it to gates, it's like having a 2-qubit entanglement gate with the error 3 nines, like twice better than 3 nines, so 0.9995. So it's still not super perfect. We try to analyze where the errors are coming. So it's better than digital. We try to analyze where the errors are coming from the purity. We see that the decoherence is still only a third of the error rate. So actually, this thing can be lowered by a factor of. So I think from this plot, it's also in the paper, but we can discuss later. You can divide this guy by 4, and you will know what is the rate of decoherence in the system. And so I think if you, and then depends on what you want to measure, like at what scale. So it's definitely not thousands of inverse G, but I think it's hard for me also to imagine a process. Okay, now I understand. So if you're like after some sort of glassy behavior and you want to study transition there, you need long times. Yeah, this I understand.
Yeah, thank you.
So I could say probably you could, like, if we do very, very good job, you could hope for like 50 to 100 inverse G, where you have control over your system is doing.
More questions? Okay, perhaps I can ask one related to what Anatoly was saying. Can you go again to the slides where you put the various pieces of Hamiltonian, the various?
Yes.
Yeah.
Sorry. Because of Zoom, this machine is not very.
Don't worry. Okay,
very
here.
fast. Yes.
Now, I think I'm getting confused because, let's say, the green term is of the same order of all the others, but the green term still contains a ZZ term that is like an interaction term. So I will say that you want to keep that term, but if otherwise you just do single particle things, right?
Oh, but in 2D.
You put it on a crazy
Okay. But still,
What do you mean via crazy lattice? 2D, yes, 2D.
but you still agree that there is no interaction in this game?
2D and
Sorry.
yes.
Okay,
2D
got
and,
it. Yeah,
2D and
got
that's my
it.
model.
Okay,
is
sorry.
Not,
Okay. More questions? Okay. So the question was because there was a term ZZ in the part that he's erasing, so I was naively thinking that this is just a single particle problem, but it's not because we are in 2D. So it's a fully general, not fully general, but it's a fairly interesting Hamiltonian, let's say. More questions? Okay, if not, we can thank Nikita again.